Hello everyone. Today we are going to talk about binary search. Binary search is a searching algorithm that operates on a sorted or monotonic search space, repeatedly dividing it into halves to find a target value or optimal answer in the logarithmic time, big O of log n. So before we talk about binary search, let's try to understand what linear search is. So let's take this example array 7, 15, 33, so on until 92 as our search space, and let's take 92 as our target. So in linear search, it starts from the rear front end or the rear end. So if you start from the front end, it compares 7 with 92, so it's not a match. Yeah, it keeps on comparing each next element in the array until it finds a match at the end of the array, which is 92 here. So when we talk about the time complexity of linear search, the worst case complexity is big O of n. The best case complexity is big O of 1, because if the target element is in the first position of the array, we get the match in just one comparison, right? And the average case is again big O of n. It's actually n by 2, but when we calculate the time complexity, we get big O of n. So when it comes to binary search, so we can take the same example here and the same target 92. So in this case, we initialize two pointers, left and the right pointer here. And so first thing we do is to calculate the mid element in the array. To calculate the mid element, we use a formula right plus left by 2. So in this case, before that I'll just note down the indexes of the array. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 elements, so the index will be until 8. And just as we discussed, so we have the left pointer on 0 and the right pointer on 8. So when we calculate the mid, we get 8 plus 0 by 2, which is 4. So mid will be here in the first iteration. So next we need to check two conditions here. So first condition is if target less than mid. So if target is less than mid, we just do a simple technique here, moving our right pointer to mid minus 1. So right equals mid minus 1, because if target is less than the mid element, which is 35, then we can 100% say that the target element will be on this side of the array than this side of the array, because it's in increasing sorted order. So in the other case, if target greater than mid, so if target is greater than the mid element, we can definitely say that the target element will be on the right side of the array from mid. So we can update our left pointer to left equals mid plus 1. So since we have already checking less than and greater than conditions, there will also be another condition, which is if target equals mid. So in this case, we got the target and it is the mid, so just need to return the mid, right? So we know these three conditions now, and formula for calculating the mid. So in this case, so the mid element, the target is greater than mid, so we just do left equals left mid plus 1. So in the next iteration, our left will be here. We don't do anything with right, so we just update the, leave the right like that. And then in the second iteration, we need to calculate our mid again, which is right plus left by 2. So 8 plus 5 by 2, which will be 13 by 2, will be 6.5. So we take the floor each time, so we get mid here around the 6th position. So the value is 90. So again, when we check the conditions, the target is greater than mid, because target is 92 and the mid element is 90. So in the second iteration, since it's again greater, so we update our left to mid plus 1. So left will come here, and then we have the right here, which will be same in the next iteration. And we just need to calculate the mid again. So mid equal to right plus left by 2. So that is 8 plus 7 by 2, which is 15 by 2, which is 7. So in this case, our mid will be on the left. So, and we check the condition: if target equals mid, no. If target less than mid, no. If target greater than mid, yeah. So we need to update the left again. So in the next iteration, we have our right here and our left here, and finally we need to calculate the mid. So mid equals right plus left by 2, which is 8 plus 8 by 2, which is 8 again. So we get our mid here, and we check our conditions: if target equals mid, return mid. Yeah, it is 92. So the total number of comparisons is the number of rows here, which is 1, 2, 3, 4. In just 4 comparisons, we got the answer. We found the number of comparisons when we used our linear search. It was around 9 comparisons, the number of elements in the array. But when we use the binary search, we just need to use 4 comparisons and we get the answer.
So what is the time complexity of binary search? Imagine the target is 35. So in the first iteration, the mid will be 35, and we get the answer in just 1 comparison. So in the best case, the time complexity is big O of 1. In average case, it's big O of log n, and in worst case, it's big O of log n again.